Hello people, welcome one and all to Jojo's Learning Club.
Hello guys, welcome back to my channel once again, Jojo's Learning Club. So today I'll introduce you to what are combinations. On my previous videos, I have listed on what are permutations, what is fundamental principle of counting, and also on factorial notations and also some theorems based on permutations, right? And on this video, I'll introduce you to about what are combinations and what is the relationship between permutations and combination. Okay, so what was permutation actually? A permutation is what? A definite order of arrangement of number of objects taken some or all at a time. That is, there are some objects and you select that objects in a definite order. And what was the formula for permutation? NPR is equal to n factorial by n minus r factorial. So what is n in this formula? N is the number of objects for which you make selection. And what is r? R is the number of selections you make from that n objects. Okay, so to understand more about combination, so let's take an example. Let's say I have three table tennis players. X, Y and Z. So these are like table tennis players. I have three table tennis players. Okay, and from these three table tennis players, I have to make a group of two. So what are the possible combinations for me? I can either make a group of X and Y, or I can either make second group of Y and Z and X, right? Can I make a group of Y and X too? No, because already you have formed a group of X and Y. This is what I said. In combination, the order is not important, because when you make a group of X and Y, it is same as making a group of Y and X. You are just adding one more combination. So this is not correct. So this is what the main difference between permutation and combination. In permutation, it is like that: when you take the first position of the two members as taken up by X, then the second position by Y, there is also one more permutation possible, that is for Y taking the first position and the X taking the second position. But this is the case of permutation. And for combination, what it is? X and Y is same as Y and X. So the order is not at all important in combination. So, okay, let's take another example. Let's say I have four numbers A, B, C and D. And out of these four numbers, I'm going to take two at a time. So, what are the possible combinations for me? AB, BC, AD, AC, AD, BC, BD and CD. These are the six combinations possible out of four letters taken two at a time. That is, I made a combination of four letters taken two at a time. And what is the answer? 6. Right. So what would be the permutations for it? You can see that AB can be also rearranged in terms of BA. Right. And also BC can be rearranged again as CB. And AC can be rearranged as also CA. I am writing this in terms of permutation. So also then AD can be rearranged in DA also. Again, BD can be rearranged as also DB. CD can be also arranged as DC. So total you can see that when you take 4P2, there is 12 permutations, and when you take the combination, there is only 6 combinations. So what is the difference? You see that for each of these combination, you can see there is a 2 factorial ways of rearranging these combination. That is, AB can be also rearranged in terms of 2 times, that is AB and BA. So what you can say that 4P2 is equal to 2 factorial into 4C2. That is, each combination in combinations can be rearranged in terms of 2 factorial ways. So let's take a bigger number so you'll get a better understanding about that. Let's say I have one more number A, B, C, D, E. And from this, I want to take 3 at a time. So what are the possible combinations? ABC, ABD, ABE. Then what else could be there? ACD, ACE, BDE. Then what? BCD. Again, it's possible. So it's only 7 here. Again, BDE, BCE, CDE. Again, let's say there are lot of combinations. So what I have done actually here, 5C3, right? And you can check that each combination, what would be the case of permutation? Let's say what would be the case here for permutation? You can rearrange this ABC also in terms of 3 factorial ways. By, if the first position is taken up by A, the second position by B, C. What is the next permutation possible? ACB. And what is the next permutation possible? BAC. The next one, BCA. Then what? CAB. CBA. That is, each possible combination can be represented in terms of, can be rearranged in 3 factorial ways. That is, for each of these combinations you have 3 factorials of rearrangement, which is not important in combinations. Why? In combination, the order is not at all important. As you have seen the first example with the table tennis players, you can see that the selection of 2 members, that is, if I'm taking a combination of 2 players, X and Y, then why you have to take Y and X? No. That is the main difference what you do in permutation and combination. In permutation is a combination, permutation is what? Arrangement of number of objects taken some or all at a time, where the order is important. So the order is given an importance, and in combinations you can see that the order is not at all given an importance. So what you can say that 5C3 is what? 3 factorial into 5P3. Permutation of 5P3 is same as 5C3. So now you got 5P3 is equal to 3 factorial into 5C3. In the previous problem you got 4P2 is equal to 2 factorial into 4C2. Let's write in terms of N and R. Let's say this is N and let's say this is R. So what would be the formula? NPR is equal to, what is this? This is actually R, right? So R factorial into NCR. And with this you have found the relationship between permutation and combination. What is that? The number of selection of indefinite or indefinite order is same as the number of combinations into R factorial permutations. R factorial of rearrangement. Or in other words, in theorem also is there, corresponding to each combination of NCR. That is, corresponding to each combination of NCR, we have R factorial permutation. That is what I proved with this one. With ABC, you can see that there are 3 factorial permutations. So if there are R number of selections, there are R factorial permutations for each combination. Okay, because R objects in every combination can be rearranged in R factorial ways. So what was the formula for this? NPR is what? N factorial by N minus R factorial, right? And what is NCR? Now we have to find the formula for NCR into R factorial. Just take this to this side of the equation. So what happens? NCR is equal to N factorial by R factorial into N minus R factorial. From this, now you have got the formula for combinations. So what is the formula for combinations? NCR is equal to N factorial by R factorial into N minus R factorial. And what is the formula for permutations? N factorial by N minus R factorial. And this formula is when the order is important. So, and for combinations, what you do? You just have to divide these formula for permutation divided by the number of permutations of, so that is R permutations of R factorial permutations you have to divide, so that you will get the formula for combinations where the order is not at all important. And now let's see some remarks about combinations. So you don't have to do the complete formula. There are some easy tricky ways which you can get the answers from combinations. So let's discuss. So in the first remark it is said that NCN. What is this NCN? You have number of n number of objects, and from that n objects you are taking all objects at a time. So what is actually the answer? N factorial. Use the formula. So what it would be? N factorial by n minus n factorial into n factorial. What it would be? N factorial by 0 factorial into n factorial. This will get cancelled, and 0 factorial, you know that it is defined as 1. So 1 by 1 is 1. So it is 1. And why you could get this answer as 1? Because when there are n objects and you take all objects at a time, you can see that their order is not important. So what happened? You have only one possible combination. So that is what, if you get problems like this, you can directly write the answer as 1. You don't have to do the entire steps. That's what the importance of these remarks. Okay. So what is the next remark saying? NC0 is equal to 1. The number of combinations of n different things, taking nothing at all. You are not taking any selection. You are not making any selection out of these n numbers. It is also same as 1. Just substitute in the formula. So what it would be? N factorial by 0 factorial into n minus 0 factorial. So what it would be? Again it will yield you 1. So that's what said in the second remark. And what is the third remark? That is, you can use this formula also in the case of 0 and 0 in between 0 also. That is as n factorial by 0 factorial into n minus 0 factorial equal to 1, which is equal to NC0, right? The formula NCR is equal to n factorial by r factorial into n minus r factorial is also applicable when you don't make any selections. So which is same as the second one itself. So they are interconnected. Okay. And what's the fourth remark say? NCn minus r is n factorial by n minus r factorial into n minus r factorial. Right? So what it would be, what is this actually? N minus r plus r. This n and n will get cancelled, and what it would become? R factorial. Right? What is this? R factorial, n minus r into r factorial. So this is actually the formula for NCR. So you get a relationship between here. NC n minus r is same as NCR. So let's write with an example. So we'll get a better. Let's say I have 10 objects. I'm going to make the combination with 2. Okay. So this is what I am written for this here, which is same as having 10C 10 minus 2. That is 10C2 is combination of 2 objects is same as selecting 8 objects. Or in other words, you can say that selecting r objects out of n objects is same as rejecting n minus r objects. That is, combination of 2 objects is same as combination of 8 objects from 10 objects. So this is a very important relationship, because in many formulas or many coming problems, you don't have to do the entire section. You can just find the answer using this remark. So please have a look on that. Okay. So what is the next formula saying? This is the fifth one. Okay. The fifth one is NCA is equal to NCB. Okay. And which is equal to, so from this you can say that it is saying that 2 combinations are same. So A is equal to B, it is said, right? So you can also write NCB as NC n minus B. That is, selecting B objects is same as rejecting n minus B objects. Okay. Rejection of n minus B objects. So here for this you substitute n minus b. So a is equal to n minus b, and from that you get n is equal to a plus b. So this is another important section. You can get your answers easily. You don't have to do the entire section. And now we are going to discuss the last and the final theorem in combination. So NCR plus NCR minus 1 is said as n plus 1 into CR. And we are going to prove that this theorem is valid. For that, let's say what it is said, NCR plus NCR minus 1 So you should get n plus 1 into CR, right? So we are going to prove this theorem. Okay, what is the formula for it? N factorial by R factorial into n minus R factorial, right? And here it would be n factorial by n minus R minus 1, that is n minus R plus 1, okay, into R minus 1 factorial. And now you can write this as, because I want to take R minus 1 common from it, so what I'm going to write it is as R into R minus 1 factorial. Again, what is this into n minus R factorial? In this side I'm going to solve again, because I want to take n minus R factorial common as common. So n minus R plus 1 factorial into n minus R factorial into R minus 1 factorial. So what are the common terms in this? N factorial is common for both the sides, and R minus 1 factorial is common. Again, n minus R factorial is also common. So I'm taking all these common terms outside. So n factorial, R minus 1 factorial, then what else is common? N minus R factorial is common. So what is left here? 1 by R. And what is left here? 1 by n minus R plus 1 is left here, right? So to solve this, I'm going to take the common terms in it. So I'm writing here again n factorial by R minus 1 factorial into n minus R factorial. So I'm going to write this as n minus R plus 1. N minus cross multiply so that their denominators are the same side. So I can do the for addition. Okay, n minus R plus 1 plus R by n minus R plus 1, n minus R plus 1 into R. Okay, so what happens? This and this gets cancelled. So you will get n plus 1 into n factorial by R minus 1 factorial into n minus R factorial, R minus 1 factorial into n minus, here one R is there, R into R minus into n minus R plus 1. So what is n plus 1 into n factorial? You can write it as n plus 1 factorial, right? Again, what is this R minus 1 into R factorial? That is R factorial itself. Again, what it is? N plus 1, n minus R plus 1, you can also write it as n plus 1 minus R, right? Right. Again, what is the next one over here? N plus 1 minus R into n plus 1 minus R minus 1. So 1 and 1 will get cancelled and n minus R. So this term and this term together, you can write it as n plus 1 minus R factorial. So what happens now? All the place with n is replaced by n plus 1. So you get the answer n plus 1 CR. So this is the theorem for the fifth, last and final section. With this, we come to an end on the explanation section on combination. On my coming videos, I will be discussing with you the entire problems and solution sections on combinations. So that's all for today's video, and let's see you on my next video. Bye bye. Take care.